Hi, I'm Fernando from UFMG in Brazil, and today we shall discuss the algorithm to solve range analysis. We had already seen a sketch of this algorithm, and in the last class we paid particular attention to the first box here, which converts a program to the standard static single assignment form. Now we look at the rest of the algorithm. First, to make the analysis more precise, we can make it inter-procedural. That means that the analysis will run across functions, passing information acquired in a function to other functions. The typical way of doing this is to connect actual and formal arguments of functions. So in this example, we are connecting variable a and the constant 10,000 with the formal parameter k, which is declared in the signature of function foo. To implement these copies, we can use 5 functions, like the figure on the right. One problem with this approach is that it's rather imprecise. Imagine we are assuming that k can be either a or 10,000 at the same time. However, k is either one or the other, never both together. Our analysis is not really context sensitive. Just to make sure that you understand why this is bad, could you stop the video and try to figure out what is the values that I could assume in this program? Does it go from 0 to 100,000 or from 0 to 100 and then from 10,000 to 100k? To make the analysis context sensitive, a common trick is to inline the function. We copy the body of the function in the place where the function is invoked. The code on the right illustrates how this approach works. Context sensitiveness improves precision, because now we can treat the arguments of function foo, that is k and n, as a pair that's either 0 and 100 or 10,000 and 100,000, but not both together. The problem with inlining is that the code grows. Nevertheless, inlining is very effective to make analysis more precise and optimizations more applicable. We now have a program in extended SSA form. We have accounted for function calls, and now we must extract constraints from this program. These are the constraints that we produce. They have this general format. They essentially explain how we can interpret each instruction in the program abstractly. I will not go over all of them. You can stop the video and read them over. To understand this notation, notice that the rules above the line must be true so that we can apply the rule under the line. We extract constraints by visiting the instructions in the program. Given the way we have renamed the variables after live range splitting, the order in which we visit instructions is not important. So for this program, we have 12 instructions. You can see these instructions on the right. We can treat each instruction directly as a constraint because there is a one-to-one correspondence between instructions and constraints. Once we have constraints, next thing to do is to construct the constraint graph. This graph will help us to solve the constraints faster. The constraint graph has one vertex for each variable in the program and one vertex for each constraint that we have extracted. And we have edges as follows. If a constraint C defines a variable v, then we have an edge from C to v. And if a constraint C uses a variable v, then we have an edge from v to c. Here's the constraint graph that we built for the constraints on the left. Notice that by uses of variables, I include futures. That is, we have edges from a variable v to any constraint c that uses v as a future. That's why we have an edge from I1 to the intersection that uses I1 here, for instance. Now that we have a constraint graph, if you remember our class about algorithms, the next thing to do is to separate the constraint graph in strongly connected components. Then we can sort these components topologically and solve constraints in the order in which they appear. For our example, these are the strong components that we can find in the constraint graph. Notice that most of the components have just one node. That's actually expected and happens a lot in practice. We must now solve the constraint system. We process each strong component in topological order. To solve strong components, we iterate 3 analyses until we reach a fixed point. These analyses are called growth analysis, which includes widening and future resolution, then something called narrowing. Let's see each one of them. The first thing is to know how each variable changes. Variables might always increase in value, or might always decrease, or might oscillate, or they may not change at all. To find this behavior for each variable, we use these 4 rules in the slides right here. In these rules, we have 2 important notations. First, we have a function e that does the abstract interpretation of each instruction, like so. Then we have the table I that holds the abstract state of each variable. Let's see what that means with examples. These rules essentially apply widening to the abstract value of each variable if this abstract value changes once. So if we notice that a variable might decrease, then we make its lower bound equal to minus infinite. If we notice that it might increase, then we make its upper bound equal to plus infinite. Essentially, we are using this lattice to find the abstract state of each variable. For instance, consider the part of the constraint graph on the bottom of the figure. We already know that the range of I0 is 0 because this variable I0 is initialized with that constant. Now let's solve the strong component that comes right after here. We start by propagating the range of I0 to I1. There is a meet through the phi function. If a constant meet is undefined, then we have that constant itself. So the range of I1 is also 0, 0 at this moment. Then there is intersection with minus infinite and the future of J1. This intersection with 0, 0 is, well, 0, 0 itself. Then there is a constraint that adds 1 to the range. So we have that the range of I2, right here, is 1, 1. We have 0, 0 plus 1. And now we need to do the meet of 0, 0 and 1, 1 to find a new value of I1 right here. So there will be a meet that I need to solve here. But 0, 0 meets 1, 1 gives us 0, 1. And we see that the range is growing on the right. So there is a rule here that we can apply. We invoke this rule that says that the right side of the range must now be infinite. You see? And now I1 is bound to the range 0, infinite. We keep propagating this range. Notice that a future before being defined is always infinite. Then the intersection yields that the new range of IT is 0, infinite. And the new range of I2 will be 1, infinite. And that's it. We found how each variable in this loop grows. Notice that these ranges are correct, but they are imprecise. We know that I1 cannot be plus infinite. We need to recover the precision that we lost. The first thing that we must do to recover this precision is to solve futures. We see the future of I1 being used as the left bound of an interval, but I1 is at least 0. So we can replace this left bound with 0 for I1. And we can also replace the right bound of this intersection with 99 minus 1. That's for J1. So J1 is limited above by 99. And then we replace it with 98, which is 99 minus 1. To solve futures, we need to know at least some limit of a variable that's used as the future. That's why having all the dependencies in the same strong components is so important. And that's why we have the dashed edges linking futures and their variables, the variables that use them. To solve futures, we use these 2 rules above. We will not go over them. I will let you stop the video and try to figure them out. After we solve futures, we need to recover the precision loss with widening. The intersections will be key to do this. Basically, we will be flowing the range of variables and constraining them whenever they pass through an intersection. In this case, we constrain the range of I1, which is 0 plus infinite, to 0, 98, due to the intersection with minus infinite, 98. The rules for performing the narrowing can be seen above. Again, that's just a way to recover the precision loss due to widening. Let's look into the first rule. This rule says that we can move from minus infinite to a constant, naturally greater than minus infinite. So this rule shows that we can shorten the left range of a variable. The other rules are similar, and you can read them over if you stop the video. Anyways, in the next step, which we are not showing, we will recover the range of I2, mapping its right side to 989. The rules on the right side are there only to ensure termination, so we can only change either minus or plus infinite. If we have other constants, then we cannot really touch them. Otherwise, we could be in a descending chain that could never terminate. Once we apply widening, future resolution, and growth analysis to all the constraints in our system, we eventually reach these solutions on the right. They are not bad, although they are still a conservative approximation of the values of the variables the values that the variables can assume. In the next class, we will see a few techniques to improve the solution a bit. And as always, until there, you feel free to write me with questions or comments. And that's it for today. See you soon with more discussion about range analysis in the next class.